All right, so I'm looking at number 3 from section 2.8. This is kind of a fun problem. We want to try to match the graph of each function a through d with the graph of the derivative in 1 through 4. So let's see if we can do this. Let's see. So if we take a look at this first one, remember what I was saying before, it's always nice to kind of look for where the derivative is 0 first. And so we see that there's two places where the derivative is 0, symmetric around the 0. And so here we see that the function, the derivative is going to be negative, then it's going to be 0, positive, 0, negative. Okay, so again, that's negative, 0, positive, then 0, negative. Do you see that somewhere in here on the 4 choices? Let's see. Well, this could be a possibility because it is 0 at 0 and 0. Whoops, can you see that? It is 0 at these two spots, but it's also 0 at the origin, so that's not a good, that wouldn't work. So that leaves 2, I think, right? Let's double check. This is negative here, and this is negative here. Then the slope is 0 there. The slope is 0 there. The slope is positive from here to here. The slope is positive from here to here. And then the slope is negative after that. So slope is negative here. Slope is negative here. Good. So this is the number graph Roman numeral 2 is the derivative of graph A. Good. How about graph B? Well, if we look to see our slopes here are going to be positive and some constant number, right? They don't change. That means it's going to be a horizontal line, and then it flips to a negative slope, and that's going to be a constant negative slope. And then this flips again to be a positive constant slope. So do we see a graph here where it's a positive, and then it's a negative, and then it's positive? Yeah, it's kind of distinctive, right? It's graph number 4. I don't know if you can see that clearly. Okay, good. We're doing good so far. How about C? Now graph C, what's happening to your derivative? Your local slopes are kind of 0, close to 0, and then they get to be some positive or some maximum negative number, and then they start getting less steep again until you get 0. And then you go positive, right? And then you hit some maximum positive slope, and then your local slopes come back down to 0 again. Do you see that relationship here? That was negative that's close to 0. You get some maximum negative point. Okay, then you go to 0 at 0. And then you go to some maximum positive point. And then you go to 0 again. Good. So it looks like graph C has derivative function 1. Good. And then, so the last one, we could do it by process of elimination, but let's just look at it as if it were a new graph. So here we see 3 zeros for the derivative, right? So here the function is positive, the local slopes are positive, and then you go local slope 0, and then local slopes are negative, negative, 0, or sorry, positive, 0, negative. Wait a minute, where are we here? This function is increasing here, so did I say negative before? I'll have to rewind the tape. Okay, but the local slopes here are positive, right? Because the function is increasing, and then it has a little plateau. Increasing, plateau, decreasing, and then it decreases all the way to 0, and then you start increasing again, and then you start decreasing at this point, right? This point corresponds to this point. Did everybody catch that? This point corresponds to that point. Oh no, now I wrote on my book. Oh well. Okay, you see the rest. Okay, let's see. The rest of these are pretty straightforward from what we've been doing before. I think you're ready to do them. You know, the trickier ones are are these algebraic definitions of the derivative. And so you just have to remember our tricks for dealing with the algebraic derivative, right? And so those were like factor in, cancel, simplify, etc. Some of these are kind of fun. Let's see, what does this say? The graph shows the driving speed, how it affects gas mileage. Fuel economy, F, is measured in miles per gallon. F is measured in miles per gallon, and speed is measured in miles per hour. What is the meaning of the derivative F prime? Sketch the graph of F prime. Well, actually, can you kind of see what's happening here in your miles per gallon? Right? So as you drive fast, as your speed picks up, right, your miles per gallon actually goes up. But then after a certain point of time, if you go too fast, right, you're going to be sucking up gas again. And so this was really the reasoning behind the speed limit caps way back in the day. Ask your father, parent, grandfather, grandmother. Remember that old song, Can't Drive 55? Well, 55 was chosen because of this. You can blame this graph for having to go slow. I don't think you guys ever went slow, but okay. We used to have to go slow. Gosh, that was back in the day. Okay, so what is the graph of the derivative? Well, remember that the graph of the meaning of the derivative, maybe we should do the derivative is the rate of change of miles per gallon per miles per hour, right? So you could kind of figure out the units from that. It's the miles per gallon per miles per hour. And so the derivative is telling you how much more miles per gallon or less miles per gallon you're getting for miles per hour, right? So the best miles per gallon you would get is about 55. After that, the economy of the gasoline goes down, right? I don't want to draw on my book. I'll let you see if you can drive. Oh, okay. At what speed should you drive if you want to save on gas? 55, but you'll probably get run off the road. Okay. So that's not very realistic. Okay. Let's take a look at this last one. Maybe this graph right here. Can everybody see that? Graph number, this 40 here. Let's see if we can take a look at this and figure out, state with reasons the number at which F is not differentiable. So if we start from here and just work our way over, negative 1 is the first point it's not differentiable, and it's not differentiable here because the function is not continuous there. Okay, we come around here. The derivative is kind of steep there, but it doesn't look like it's going vertical yet, right? And then if we come up, the derivative is going to 0, and then it's, oh, there's a sharp point. So here the function is also not differentiable because we have a sharp point. So the limit from the right is going to be different from the limit from the left. Very good. Did you get those so far? This is kind of a fun one too. All of these. Which one should we do? Oh, let's do 45. Can we figure out which function is, so I've got 3 graphs, A, B, and C. One of these functions is the curve. The other is velocity, which is the derivative. And the other is the derivative of the derivative, F double prime. Which one is which? So let's just look at curve A first. So we can ask the question, is the derivative of curve A present in your graph? If it were, the function would have to cross 0 here, but none of them do, and it would have to also cross 0 there, which none of them do. So therefore, the derivative of curve A is not present. So therefore, what will curve A have to be? I think you see curve A is probably going to have to be the acceleration, right? The second derivative. Okay, so now we can look at curve B and say, is the derivative of curve B present? Well, the derivative of curve B would have to be The curve B is it will have positive local slopes here. It'll be 0 there, and then it'll be negative. So is there a curve that's positive up to this point and then negative after that? I think you see that that's curve A. So if curve A is the second derivative, curve B must be the first derivative, and curve C then must be, by process of elimination, the original function. Very good. And so you can see that B is the derivative of C, right? Because it has some maximum positive number before it goes back down to 0. Good. Lots of good examples, or lots of good problems in this section. Let's see. I think I may leave the rest of these for you to check out. If you do have questions about these, sign up for a time we can meet, or you can send me an email. I will talk to you later.